Have you ever really thought about how your remote control just works? Or how your phone seems to magically know what you want it to do? Well, it all comes down to a kind of secret language, the language of electricity, and specifically DC circuits. And today, we're going to learn the basics of how to speak it.
Yeah, what is going on in there? It's not magic, it's electricity. But it's a very specific kind of electricity that flows in just one direction, kind of like a river flowing steadily down to the sea. And that constant, predictable flow, that is the absolute key to understanding how all these amazing gadgets actually do what they do.
And that one-way flow is exactly what we call a direct current circuit, or, a DC circuit. The water pipe analogy is honestly perfect. You've got a pump, it pushes water in one single direction, and that's it. It's a simple idea, but it's so powerful. It's the foundation for everything we're about to cover.
All right, so now that we know what a DC circuit is, let's talk about where all that power actually comes from. I mean, you can't have a river without a source, and you definitely can't have a circuit without a heart to get it all pumping. So that pump we're talking about can be a few different things. You've got your everyday cells, like the AAs you pop into your remote, and when you group those cells together, well, that's what a battery is. Or if you're plugging something into the wall, you're using a power supply. Think of that as like a super smart translator that takes the wild electricity from the outlet and turns it into a gentle, steady stream that your gadgets can actually use.
Okay, so once you have power, you can't just let it run wild. That would be chaos. You need to control it, and that's where our passive players come in. We call them passive because they don't create their own power, but man, they are absolutely essential for telling that power where to go, how fast to move, and what to do.
First up, let's meet the resistor. The resistor is basically the traffic cop of the circuit. Its entire job, its whole reason for being, is to slow things down and control the flow of electricity.
You see that little zigzag line? That's the universal symbol for resistor, and it's perfect, right? It visually tells you exactly what it does. It's like a speed bump for electricity, making sure the current doesn't get out of control.
So, going back to our water analogy, a resistor is just like a narrow section in the pipe. And just like friction creates warmth, a resistor actually turns some of that electrical energy into heat. That's why your phone gets a little warm after a long phone call. In some cases, like a toaster, that's the whole point. The resistor is designed to get super hot and glow, just to toast your bread.
Next up, meet the capacitor. Now, if the resistor is a speed bump, the capacitor is kind of like a tiny, super fast water tank. It can fill up with energy almost instantly and then dump it all out in one quick burst when it's needed.
So those two parallel lines in its symbol, they actually represent two little metal plates with a tiny gap between them. And that's where all the magic happens. The capacitor stores energy right in that gap, acting like a tiny electrical reservoir ready to go at a moment's notice.
You can almost think of it as a shock absorber for electricity. It smooths out any little bumps or dips in the power, absorbing extra energy and then releasing it when there's a drop. This makes sure all the other sensitive parts get a nice, steady, reliable stream of power.
And our final key player for today is the diode. The diode is the official bouncer of the circuit. Its job is to stand at the door and make absolutely sure that electricity only flows in one direction. No exceptions, no turning back. The symbol here is a perfect giveaway. It's literally an arrow pointing at a wall. Electricity can flow in the direction of the arrow, no problem. But if it tries to turn around and go the other way, nope, it hits a dead end. It is a strict one-way street.
And this one-way street function is incredibly important. It's what protects sensitive electronics from getting fried if you accidentally put the batteries in backwards. Plus, it plays a key role in converting that chaotic, two-way alternating current from your wall outlet into the calm, one-way direct current that all your gadgets need to survive.
So let's recap. We've met the power source and our three key players, the resistor, the capacitor, and the diode. Now it's time to put them all together and see how they actually speak to each other to get things done. These symbols, they're not just drawings. They are the universal alphabet of electronics. An engineer in Tokyo can look at a diagram made with these symbols, we call it a schematic, and know exactly how to build the same thing as an engineer in Toronto. It's pretty amazing, kind of like a musical score, but for electricity. And building a circuit is really as simple as 1, 2, 3. First, you start with your power source. Then, you add your components, your resistors, capacitors, what have you, to control the flow. And then, and this is the most important part, you have to complete the loop. If the electricity can't get back to where it started, it's a dead end. Nothing happens. Okay, so now you know the basic building blocks. But in the real world, it's not just about knowing what the parts do.
It's about choosing the right parts for the right job.
I mean, let's just take our friend the resistor. You could use a really cheap carbon film resistor in a simple kid's toy and it would work just fine. But what if you're building something like a pacemaker? You're definitely going to want a more expensive, more reliable metal film resistor for that. It's a classic trade-off between cost and performance, but sometimes that choice is, literally life or death.
And it's not just about cost versus reliability anymore. Engineers also have to think about the environmental impact. Is it better to use a cheaper component that might end up in a landfill, or a slightly pricier one made from more sustainable materials? These are the kinds of tough balancing acts designers and engineers have to deal with every single day.
So here's the bottom line. The next time you pick up your phone, just remember, every single tiny piece inside has a specific job to do. It has a universal symbol, and it was chosen after a really careful balancing act between cost, reliability, and its impact on the planet. It's this tiny, incredibly complex ecosystem, living right there in the palm of your hand.
And just like that, you've learned the secret language of the digital world, the basic grammar that powers pretty much everything around you. So now that you know how it all works, what are you going to do with that knowledge? The possibilities, well, they're pretty much endless.